Hello everyone and welcome to Control Engineering tutorials in MATLAB. In this tutorial we explain how to properly compute phase and gain margins in MATLAB. Let us immediately start. Here, for presentation clarity and for brevity, we will consider a particular form of a transfer function. However, everything explained in this tutorial can be generalized to arbitrary forms of transfer functions of linear systems. Our transfer function has this form. W of s is s plus 30 over s to the power 3 plus 12s squared plus 20 plus 15. To define this transfer function in MATLAB, first we need to define two arrays. The first array, and I will call it num, is the array that will store the coefficients of the polynomial in the numerator. The coefficients are 1 and 30. Then we need to define another array storing the coefficients of the polynomial in the denominator. Let's collect these coefficients. They are 1, 12, 20, 15. Then, let me just undo this. Then, to define a transfer function in MATLAB, we will simply use the function tf, and we will specify as the first argument the array storing the coefficients of the polynomial in the numerator, and the second input argument is the array storing the coefficients of the polynomial in the denominator. So here it is. So let's do this in MATLAB. First of all, I usually like to start with clear. This will clear the workspace, and CLC. This will clear the command window. Then let's define the numerator array. It is 130. And let's define the denominator array. The denominator array is 1, 12, 20, and 15. Okay, let's define our transfer function. W is tf num comma den. So here's our transfer function. Let us verify that everything is okay, and here is the transfer function in the MATLAB workspace, and here is the analytical form of the transfer function. Good, let's continue. There are several approaches, or better to say methods, for identifying and computing gain and phase margins in MATLAB. The first approach is based on a Bode diagram. Consequently, let's generate a Bode diagram. First of all, let's define a figure, and to compute, or better to say to generate a Bode diagram in MATLAB, we use the function Bode, and we specify our transfer function. Below the Bode function, I will simply call grid to generate a grid. Okay, so let's evaluate this code, and here it is. Here's our Bode diagram. The easiest way to compute, or better to say to identify the gain and phase margins, is simply to right-click over here, then click on characteristics and click on minimum stability margins, and you will immediately see the result. So how do we identify the phase margin? To identify the phase margin, we are looking at the magnitude plot, and we are looking for a point at which the magnitude plot crosses 0 dB line. 0 dB line is actually a line in logarithmic scale. In the normal scale, this corresponds to unit circle. Then, it's somewhere here. Now, if we vertically go down, and if we find intersection of the vertical line starting from this intersection point and ending at the phase plot, we will see this point. And this point precisely is a point at which we can read the phase margin. And we can see the phase margin is 67. Basically, the phase margin is the difference between 180 and the absolute value of the phase at this point. The phase at this point can be read. And this difference over here, let me denote it like this, that is from here to here is actually 67 degrees. And that's our phase margin. Here it is. How about the gain margin? How is the gain margin defined? Gain margin is identified by looking at the phase plot. We are following the phase plot and we look at the point where this phase plot crosses 180 degrees, or better to say minus 180 degrees. Then we vertically go up and we search for the intersection with this vertical line with the magnitude plot. And here's the point. And you can see that the gain margin is 21.9. Let me move this here. The gain margin is actually this distance in the logarithmic scale. And this distance is actually 21.9. So our phase margin is 67 and our gain margin is 21.9. That's it. This is the simplest approach based on the Bode diagram. Let's explain other approaches. Another approach is based on the Nyquist diagram. Let's explain the second approach. To generate a Nyquist diagram, let's first define a new figure. This will be figure 2. And over here, let's type Nyquist. And let's specify our transfer function. Okay, the Nyquist function will generate a Nyquist plot. And then after that, let's add a grid. Now let's evaluate this piece of code. And let's be patient. Here it is. Here's our Nyquist diagram. Perfect. Again, to compute, or better to say to identify the gain and phase margin, we do again the right click, we do characteristics, and we click over here on minimum stability margins. And you will see immediately 2 points. Now if you zoom in this graph, let's do this, you'll see better these points. This blue line over here is our Nyquist plot. The phase margin is found as the intersection of our Nyquist plot and the unit circle. This is the unit circle. In this graph actually looks as an ellipse, however, it is a unit circle because my axes are not equal. So here's the point. And we can see that the phase margin is 67 degrees. This is actually the angle that this line over here, the intersection line, going from the intersection point to 0, creates with this axis. And here's the angle. And this angle is actually 67 degrees. Perfect. Now, how about the gain margin? The gain margin can be found like this. Let me just erase this. Now, let me zoom in this part over here again. To identify the gain margin, we are looking at the intersection of our Nyquist plot, that's represented by this blue line, with this horizontal line. And here is the intersection point. Now let me just click here again, so I can select this point and you can see the gain margin is 21.9 and it's at frequency 5.7 radians per second. And moreover, you can see that the closed loop system is stable. The third approach for computing the gain and phase margins is not graphical. Namely, we can use the built-in MATLAB function for computing the gain and phase margins. The name of the function is margin. The input of this function is our transfer function. And what are the outputs? The first output is our gain margin. I will denote it like this. The second output is our phase margin. The third output is actually the frequency at which the gain margin is measured. I will call this frequency as Fg. And the fourth input is the frequency where the phase margin is measured. I will call this frequency as Fp. Let's evaluate this function and let's see the results. Okay, first of all, let's look into the gain margin. The gain margin is 12.5015. However, on our Bode diagram and similarly on the Nyquist plot, we can see the following. We can see that the gain margin is 21.9. So why this Bode plot brings this value and our function computes this value? Is there an error? Well, there is no error. Note over here that the gain margin is expressed in dBs, that is in decibels. However, this gain margin value is expressed in the standard scale. Okay, so to show that this is correct, I will compute gm log as 20 times log 10 of gm. This is how the magnitude is actually transformed. And let's see the result. And clearly you can see 21.93, and that's precisely this value over here. So there is no error. Okay, how about the phase margin? So here's the phase margin, and the value is 67, and that's precisely what we see on our Bode plot. So let's double check the frequencies. First of all, let's see Fg. This is the frequency where the gain margin is measured. It's 5.7, and over here we can see 5.7, and let's check the frequency at which the phase margin is measured. This is Fp, and we can see that Fp is 1.53, and that's precisely the frequency over here. And that's it. Simple as that. Okay, that would be all for today.